Good morning, everyone. We're going to start with question 12. A fair coin is tossed 10 times. The probability correct to 4 decimal places of getting an 8 or more heads is. This is from the VCAR methods exam. So take a moment now, please pause the video and try to complete this question. Hopefully you've completed it. The answer is C, and 71% of students answered this one correctly. It's very much on what we learnt last lesson. So if we've got a fair coin that's been tossed 10 times, then this becomes my N, my number of trials, and then the probability correct 4 decimal places of getting 8 or more heads. So what I'm looking for is probability X, where X is the number of heads. I want 8 or more. Now, of course, this is a CAS exam. Please don't waste your time working this out by hand. It'll go straight into your calculator. So in the calculator, we'll use binomial CDF because it's more than one that we're looking at. And our number of trials is 10. Our probability of success, because we're talking about a fair coin, then the probability of getting a heads or a tail is always 0.5. And my lower bound is 8 and my upper bound is 10. So when you type that into the calculator, you'll get C. So that's the answer. All right, chapter 14b, graphs of binomial functions. So today what we're doing is we're learning about the mean, variance, and standard deviation for the binomial probability distribution. And what you need to be able to do is find the expectation, variance, and standard deviation of a binomial distribution, use the 95% interval to find data, and find unknown variables such as the number of trials or probability using the mean or the variance. Hopefully a lot of these words are quite familiar to you because it's everything that we just did with our discrete random variables, but now we're specifically looking at the binomial probability distribution with all of these, expectation, variance, and so on. Before we get there, we're going to just talk about the graphs of the binomial probability distribution. So we have looked at graphs before in terms of probability, and the binomial probability distribution also has a particular type of graph. What we do is we graph N, so the number of trials, versus P, the probability. And what we're going to do is we're going to explore what or how the graph changes based on the number of trials and probability. So for this example here, what we can see is that we've got 20 trials. So our X in this case is the number of trials. And then on this axis, we have the probability. Now what we know is that the probability is 0.2. So you can see that when the probability is low, if I have 20 trials, then I likewise expect a lower number of successes, with the actual number of expected successes being 4. Now, where did I get this number from? Think about it like this. If I have a 20% chance of something occurring and I have 20 trials, well, 20% of 20 is equal to 4. So I would expect that 20% of the time that I do these number of trials, I will get a success, which is 4. So in general, you can think about if I've got a low probability, I've got a lower chance of success, and this is what we call positively skewed. It's skewed towards the right-hand side. So that's what our positively skewed looks like. All right, graphs of the binomial for a probability of 0.5, very similar to before. If I have a 50% chance of success and I have 20 trials, then you would imagine that I would expect I would get 10 successes. So half the number of trials should be a success. Now, obviously, as we know in the real world, not everything is going to be as we expect, but it'll be somewhere around the middle. So I should expect that the majority of my successes lie somewhere in the middle. So that's why we say between 6 and 14. This is what we call a symmetrical graph. It's not skewed either to the right or to the left. And as you can imagine, for the last one, if I have a higher probability, I have an 80% chance of success, 0.8 probability, out of 20 trials, then I expect to get about 16 successes in the perfect world, but it's not, so it'll be just somewhere that's around here, a higher chance of success. So you can see that we generally will observe 12 to 19 successes if I've got such a high probability out of 20 trials. And this type of graph is what we call negatively skewed. It's skewed to the left. So you can see now how the probability affects the number of successes in our binomial distribution. Now, what we can do from these graphs is grab a bunch of statistics, and you will have noticed I kept using the word how many successes do I expect? And it's as simple as just figuring out the probability multiplied by the number of trials. So if I have a 50% chance of success and I have 20 trials, then I'm going to expect to get 10 successes. So how do we work that out? It's the number of trials multiplied by the probability, and that's how I find my expected value, which is the mean. So notice that that's very different. Well, it's not so different, but it is a different formula, I suppose, than when we did the discrete random variables, where you multiplied x by the probability and then added them all together. So it is a different way of finding the expected value, and it only works for this particular binomial probability distribution. The variance, which is to find out the spread, is the number of trials multiplied by the probability, but then also multiplied by the probability of failure. So that's your variance. And what we actually care about is more so the standard deviation, where you just take the square root of that. So these are the three formulas you need to know for your binomial probability distribution. And now all we're going to do is go ahead and apply those. One of those applications is about this interval of the mean minus 2 times the standard deviation and the mean plus 2 times the standard deviation. Remembering this Greek symbol mu means the mean, and this Greek symbol sigma means the standard deviation. So what we have is the mean, and then the standard deviation is a specific interval that we work out that gives us a certain percentage of how much my data lies in. So if I move away one standard deviation from the mean, I can say that 68% of my data is going to lie within this range. So 68% of my successes are going to lie within this range. If I look at 2 standard deviation, 95% of my successes should lie within this range. And then if I look at 3 standard deviations, then 99% of my data is going to lie within this range. What we're interested in methods is this one, 95%. Because we want to make sure that if we have a certain range of whether it's successes or whatever it might be, that 95% of it lie within this range. We don't want it to be too far out. So we want to make sure that 95% of our data lie within 2 certain values. And if it doesn't, then it means, whatever the application is, that person needs to go back and look at how, the risk factors or whatever else that is affecting that interval. But that's more of an application outside of methods. All you'll be required to do is really just work out that interval and interpret it, as we'll see in a question later on today. All right, let's go ahead and apply all of this. So example 7, find the mean variance and standard deviation of x if x is a binomial distribution where the number of trials is 20 and the probability of success is 0.4. Really, this is just a matter of applying all of our formulas. So we've got to do 3 things: the mean, the variance, the standard deviation, and all we need to do is find all of those formulas from our previous slides and apply them. So the expected value is the number of trials multiplied by the probability. So that's 20 times 0.4, which is going to be 8. So if I do 20 trials with this probability, I will expect to get around 8 successes. Then I'll find my variance, which is a description of spread. So that's n times the probability of success times the probability of failure. So n is 20, probability of success is 0.4, and then probability of failure would be 0.6, because success and failure must always add up to 1. When you work that out, that's 4.8. So that's a value that's describing the spread for me. Now, what I'm more interested in is the standard deviation, and that is simply the square root of the variance of x. And when you take the square root of 4.8, you get 2.19. All right, next example 8. We've got a x, which is also the binomial distribution. NP has a mean of 12 and a variance of 4. Find NP. So this time we're kind of working backwards. So what's the information that I know? If I've got a mean of 12, it means that my expected value is going to be 12. And if I've got a variance of 4, it means that, well, the variance is 4. If I think about it in terms of my Greek letters, this is the mean, and then the variance is sigma squared. Okay, so that's that standard deviation squared. That's how we represent both of them. Now it's just a matter of applying the formulas. So let's think about my expected value. Now the formula for the expected value is n times p. So they'll have np is equal to 12. And then the formula for the variance is np times 1 minus p. And in this case, np times 1 minus p is equal to 4. Now, what we can do is, of course, we can rearrange to get one letter by itself and substitute in, but there's actually something easier that we can do. In this case, np equals 12. Well, I can see that there's an np there. So I can go ahead and just substitute that straight into there. So that'll be 12 times 1 minus p equals 4. I'm going to go ahead and divide now by 12. So 1 minus p is going to be 1/3. And then what I can do is take the p over to this side to make it positive and the 1/3 over to this side. So that will be, I'll just continue on this side, p is equal to 1 minus 1/3, which is 2/3. So my probability of success is going to be 2/3. Now, once we've done that, I can go ahead and substitute p back in to be able to find n. Just making a little bit more space for myself. So I'm going to sub that back into the actually, probably the expected number formula. That'll probably be a little bit easier. So I know that NP is equal to 12. I know that P is equal to 2/3. So the way you get a fraction over to the other side is by multiplying by the reciprocal. So 12 times 3 on 2 is going to be 18. So this gives me that the number of trials is 18 and the probability of success is 2/3. So it's a matter of just subbing in and solving, but this is one particular technique that you can use where you just substitute both NP into the formula. All right, next example. So we're at an election, 37.5% of the population is going to vote for the Labor Party. Now, this is a very important number. This is going to be my probability of success. So the probability that they're going to vote for the Labor Party is 0.375. And just for our purposes, this is actually equal to 3 on 8. You're not necessarily expected to know that number, but I think once you see the decimal 0.375 enough times, you'll start to recognize that it's equal to 3 on 8. If 8 people are surveyed from the population, how many would you expect to be voting Labor? So here are the number of trials that I have, and is going to be equal to 8. And what it's asking me is for how many people I would expect to be voting Labor. So it's asking me for the expected value, which I know is equal to n times p. So the number of trials is 8, and the probability of success is 3 on 8. And then I can cancel out. Now, of course, if you did not recognize that it is 3 on 8, that's totally fine. You can just use your calculator and you'll get the exact same number. I just wanted to change it to 3 on 8 because I know that I can cancel out like that. All right, the next question says, find the probability less than the expected number will in fact vote Labor. So we want less than the expected number is going to be successful. So what I'm looking for is the probability that we will have less than 3. So that means I want the probability of 0, 1, or 2. So that's the same as saying less than or equal to 2. Now, why would I change that? It's just to ensure that we don't get confused when we type this into the calculator, because remember, the calculator needs the lower bound and the upper bound of included values. So 3 would not be our upper bound because it's not included, but 2 is. So that's why I always like to rewrite it, but in terms of what is included. So this is going to be my binomial CDF because it's an interval. My number of trials is 8. My probability of success is 0.375 or 3 on 8. My lower bound is 0 and my upper bound is 2. When you type that into the calculator, you should get 0.3697. All right, we're up to our last example. So the probability of contracting influenza this winter is known to be 0.2. So I can already highlight that and write probability equals 0.2. Of the 100 employees, more information, number of trials I've got is 100 at a certain business. How many would the owner expect to get influenza? So what we're asked to do, first thing we're asked to do is to find that expected value. So I'm just going to make a note of that for myself so that I can recognize as something that I need to do. Find the standard deviation. Okay, so that's the next thing that I'm required to do. So step 2 is to find the standard deviation of the number who will get influenza and calculate the mean plus 2 standard deviations. We then need to interpret. So there's lots of things that we're needing to do. So I'm going to calculate it. Actually, I'm going to put that under the word calculate, and then I need to interpret. So I'll just go ahead and highlight all these words. Okay, so I'm just going to split my page up into 4. Hopefully that's enough space. Calculate and interpret. So it's really important that you split your question up, one that has so many things that you need to do, up into portions like this so that you don't forget to do something. And I know that I am the number one person to just forget half a question. I'm sure many of you have already experienced that in class. I just forget to do the last part. So this really helps me to make sure that I'm not going to forget to do something. All right, let's go ahead and do all this. So first of all, we're finding the expected value, which I know is n times p. So the number of trials is 100 and the probability of success is 0.2, sorry. So 100 times 0.2 is going to be 20. So I will expect 20% of them to get influenza. Next, it's asking me to find the standard deviation. So the standard deviation is equal to the square root of np times 1 minus p. So that's the square root of the variance. So I'm going to go ahead and plug all my numbers in. So that's 100 times the probability of success times the probability of failure, which is just 1 minus 0.2. We're not dividing anything. We are taking the square root of that. Now, this is a question that I have not done beforehand. So I need to take a moment now to work that out for you. You should also be typing that into the calculator. We actually get a lovely number. 4. How nice is that? Okay, so that is the standard deviation of 4. So next it asks me to calculate the mean plus or minus 2 standard deviations. So we're looking for that interval. So I'll do the mean minus 2 standard deviations. I guess it gives us a square bracket, and then the mean plus 2 standard deviations. So remembering that the expected value is the mean. All right, so the mean is 20 minus 2 times the standard deviation, and then 20 plus 2 times the standard deviation. So 20 minus 8, I'll just pick that up. 20 minus 8 is 12, and then 20 plus, sorry, that's 4, isn't it? I just calculated that in my head. And then 20 plus 8 is 28. All right, now finally, what it's asking me to do is to interpret this interval. So what does this mean, 12 to 28? Remember, I expect 20 people to get influenza because that's 20% of 100. But because we're not in a perfect world where all of our trials are going to work out perfectly, then there has to be some sort of a range. So remember, with our binomial graphs, we had our expected value as the majority of successes, but then we did have certain numbers around it. So within 2 standard deviations is when I get 95% of my data. So that would mean that 95% of the number of people that will get influenza will be between 12 to 28 people. Okay, so I am expecting 95% that it's going to be between 12 and 28. It could be 30, but that's outside of my 95% expectation. That's what that means. So I'm pretty sure, 95% sure, that it's going to be between 12 to 28 people that are going to contract influenza. And I feel like I probably could have worded that answer there. 90% of the number of people that will get influenza will be between 12 to 28. I probably did not need to reword the word people to rewrite it. But that's what it means, okay? 95% of people that will get it, it's going to be, there's a 95% chance that it's going to be between 12 to 28 people. And that's probably an even better way to write it. 95% chance that it's going to be between 12 to 28. Okay, so that's it for this example, for this chapter rather. It's 14b. Please go ahead and complete your exercises for today.